Okay. So we have been discussing perturbation theory. Give me a minute. So we discussed time independent perturbation theory. Or it's also called stationary state perturbation.
Sorry, sir, we can't hear you.
Okay, so what I have been discussing is time independent, or it is also called stationary state perturbation theory. Okay, so we had talked about two cases, degenerate and non-degenerate and degenerate case. So in the case of non-degenerate case, non-degenerate spectrum, then if your H can be written as H0 plus some lambda times H prime. So this lambda is what we call as small parameter. And we have assumed that this H0 N0 is equal to En0 N0 can be exactly solved. Can be exactly solved. That means we know these things. And then we have assumed that Hn, that is the total Hamiltonian times total Hamiltonian's eigenstates, cannot be exactly solved. Okay, so we are going to express this En as En0 plus lambda times En1 plus lambda square times En2 and so on, and our N as N0 plus lambda times N1 plus lambda square times N2 and so on. Okay, so Enj and Nj are jth order corrections. Jth order corrections to En0. Okay, and if you include up to jth order correction, you are going to get an approximate value of En, not exact value. Exact value means you have to introduce all orders of perturbation. And we had seen in the last class that the first order correction, okay, first order correction is obtained for the energy En of 1 as simply the expectation value of the perturbation Hamiltonian in the unperturbed eigenstate. So this is your first order correction in the energy. Similarly, first order correction to the state was obtained as sum over m not equal to n. Okay, and you have m0 h prime n0 divided by en0 minus em0. This is the coefficient of expansion into m0. So this is how the state is modified. Okay, so this is unperturbed state, and this is the first order perturbation correction and second first order perturbation in energy and first order perturbation correction for the state. Now we also have shown that second order correction for energy, as we had shown that En of 2 is equal to sum over m not equal to n m0 h prime n0 modulus square of this divided by en0 minus em. Okay, we have shown this in the last class, so I'm not deriving them again. So I'm just giving the expressions. And as I told you that these expressions, if you know, or if you write them in a sheet of paper, then you can actually use them to solve problems. Okay, so let us try to uh, solve some problems. So let's say the first problem that I want to solve is that I have a particle in a one-dimensional box of size, let's say 0 to L, and we know energy eigenvalues and energy eigenfunctions for this, correct? So for this problem, we know energy eigenvalues are given by n square h bar square pi square by twice ml square, and energy eigenfunctions are going to be uh, root 2 by L into sine n pi by L into x. So this is basically unperturbed, unperturbed problem that is solved. Okay, so if you want to, maybe you can write it as en0 and psi n0. Okay. Just to say that this is an unperturbed. Now let us say that there is a perturbation. So this is perturbed by h prime, okay, which is equal to, let us say, some v naught into delta of x minus L by 2. There is a perturbation like this at x equal to L by 2. There is a delta function potential. Now you ask a question, what is the first order correction in energy? Okay, what is the first order correction in? So what is En1? Okay, so go back to this expression of En of 1, and now we have to write this in the coordinate basis. Okay, so now what do we write? This En1 is an expectation value, right? So expectation value will be integral 0 to L psi n star of x into h prime operator acting on psi n of x dx. If I want nth eigenstates, this is what it is. Now you can write this as 2 by L integral 0 to L. Okay, so h prime is, I will put this v naught outside, delta of x minus L by 2 into sine square n pi by L into x dx. So since there is a delta function integration, the integral is very easy to perform. So 2v naught by L into, so what is the expression? So that will be, wherever x is there, you have to put sine square n pi by L into L by 2. Okay. So what is that? This L and this L will cancel. So you have 2v naught by L into sine square n pi by 2. Correct. So this is your first order correction for 1. The first order correction for nth energy level. Now, for example, if you take ground state, so let's say you take a ground state, that is E1 of 1. E1 of 1 is n equal to 1, so sine pi by 2 is 1. So sine square pi n pi by 2 is also 1. So this is equal to 2v naught by L. What about first excited state, that is E2 of 1? For E2 of 1, n is equal to 2. So that means this becomes sine square pi. Sine pi is 0. So sine square pi is also 0. So this correction will be 0. If you take n equal to 3, that is E3 of 1, if you take, this will become what? 3 pi by 2. Sine 3 pi by 2 is minus 1, but sine square is there, so it will be 2v naught by L. So you can see that this En, the first order correction in the energy, will be equal to 2v naught by L for n is equal to 1, 3, 5, etc. all odd quantum numbers, and 0 for n is equal to 2, 4, 6, etc. all even integers. So this will be our energy correction. Our energy correction is, there is a correction for odd values and there is no correction for the even energy levels. Okay. So this is something which we have calculated. Now you can ask what are going to be the wave functions, that is correction to the wave function. So what will be the energy? So up to first order.
அழுது உக்காடுறா அதான்டா.
Hello. What's the question asked in English? What was the question? Up to first order correction, your energy En is approximately En0 plus this En1. That is, I am assuming that we will use a full perturbation. That means I set lambda is equal to 1. In which case, this will be En0 plus En1. So En0 is already known to us, and En1 is given by this expression. Okay, if V naught is positive, then if you had these levels, let's say these are the energy levels of the particle in a one-dimensional box, then this will increase. Okay, so maybe let me draw the new levels like this. So this will increase, this will not increase, this will increase, this will not increase, and so on. So the spacing is different. Okay, earlier there was a spacing of this is going like n square. Now there is a some change in the level. So this is for h naught, and this is for h naught plus h prime. Okay. Now let us say that you are interested in asking what happens to the state. Okay, so that means you have to calculate, look at this expression again. So we have used this expression to find out the first order correction in the energy. Now let's look at this expression. So that means, so in the coordinate representation, if I so first order correction for the state, correction for psi n of x. Okay, so for the state, so you can write down psi n of x, sorry, your psi n1 of x can be written as sum over m not equal to n, and we have um, integral 0 to L dx psi m0 of x into h prime into psi n0 of x. Okay, so that is the divided by en0 minus em0. So this is the coefficient. Okay, so you have to integrate this to get this coefficient. Okay, so you do this integration and then you put that as a coefficient to psi m0 of x. Okay, so we have to solve this integral. So we have to solve integral 0 to L dx psi m star of x into, of course, there is a v naught into delta of x minus L by 2 into psi n, so there is a 0, this is the zeroth order wave functions of x. So that is equal to 2v naught by L integral 0 to L dx delta of x minus L by 2 into sine m pi by L into x into sine n pi by L into x, which is equal to twice v naught by L into sine m pi by 2 into sine n pi by 2. Correct? So that is what, wherever x is there, you put L by 2. Sine m pi by 2 into sine L pi by 2. Okay. So now you know that, so you can see what happens to this coefficient. So I will call this as, so we will call this as Cm. Okay, so Cm is equal to this. Now n is fixed. Suppose if n is equal to, if n is even, then there is no coefficient, right? So if n is 2, 4, 6, etc., that implies Cm is equal to 0 for all n, because this sine n pi by 2 will become 0. On the other hand, if n is equal to 1, 3, uh, let us say if n is equal to 1, that implies your Cm can be written as 2v naught by L into sine m pi by 2. Correct? So now what happens? Your now if n is equal to 3, if n is equal to 3, that implies your Cm is equal to minus 2v naught by L sine m pi by 2. Now if m is equal to even, then this will be 0. Okay, so this will be equal to, you can say 0 if m is equal to 2, 4, etc. And 2v naught by L into, how do I write? The odd numbers, if it is 1, it is pi by 2. If it is 3, it is minus pi by 2. So you can say this is equal to minus 1 to the power um, 2n plus 1. Is that correct? So n is equal to 1, n is equal to 3. Okay, so what I should write is, okay, maybe let me write it explicitly. If m is equal to 1, 5, 9, etc. And this is equal to minus 2v naught by L if m is equal to 3, 7, etc. That is alternate odd integers, it will become like that. Same thing is true here. This will become minus and plus will interchange its sign. So what does that mean? That means, suppose if I consider, let us say, you want to understand what is the first order correction to the ground state, wave function. That means your n is equal to 1, which implies your coefficients are is equal to 2v naught by L into sine m pi by 2. Okay, so that means your wave function psi n1 of x will be equal to, suppose if I take 1, so that will be 2v naught by L into sine, of course there will be a root 2 by L, because that wave, it will come with the wave function, and sine m is equal to 1, right? So sine pi by L into x. Now m is equal to 2, it will be 0. M is equal to 3 will be, so root 2 by L I will write it as common, minus 2v naught by L into sine 3 pi by L into x, and 5 pi. Okay, 5 pi is again plus 1. So plus 2v naught by L into sine 5 pi by L into x. Now 7 pi will be minus 2v naught by L into sine 7 pi by L into x. So you'll have all odd multiples of pi by L, but then with alternate signs, plus and so on, so on. So this is your first order correction. Okay.
Sir, you forgot EM minus EN in the denominator.
So that will come as an extra term. That will be, so for every term it will be different. So for that it will be En. So n is not equal to m. So that means this term will not be there. We have to only try. So m equal to 1 term will not be there. Okay, so we have to try m equal to 2 onwards. So then this will have E. So E10 minus E20, and this will be, it's not E20, this is E30, and this one will have E10 minus E50, and this will be E10 minus E70. So So this will be an infinite series, but this is going to be your first order correction. That means your actual function will be the unperturbed wave function plus all these terms. So this turns out to be the first order correction for this simple looking potential. Okay, so that is what we have to, that is how we have to calculate given the perturbation. Okay, so let us look at another example. Suppose let's say that I have, um, let's say that I have a harmonic oscillator. So consider my unperturbed Hamiltonian is e square by 2m plus half m omega square x square. Okay. Now, let me say that I have a perturbation which is some kind of some alpha times x. Okay. It is linear in x. Now, if you ask, so you know all these energy levels. So En0 will be equal to n plus half into h bar omega. And then you have these energy eigenstates, which are the number eigenstates n. And these are known. Okay, so I will call this as n0. So this is known. Now, if you want to get first order correction in the energy, then it is basically your n0 plus x operator, alpha you can pull out, and then n0. Correct? But what will this be equal to? This is equal to alpha into whatever some coefficient. Maybe if you remember correctly, it is m omega by 2 h bar into n0, and x can be written as a plus a dagger n0. But what will this be equal to? A dagger will raise this to n plus 1 and a will lower it to n minus 1. So as a result, you will get this to be 0. That means there is no first order correction. Now, does that mean that there is no correction at all for the energy? That does not mean. So first order, up to first order perturbation, the energies are not changing. Now you can ask about second order correction in the energy. Okay, second order. Now what second order correction? So we have to use that formula which we have written here, this formula. So for that, what you have to do is you have to calculate. So you know that second order correction is given by sum over m not equal to n. So m0 h prime n0 modulus square of this divided by en0 minus em0. Correct. So for that we have to calculate this quantity, that is m0 into alpha x cap to n0, which is nothing but alpha into square root of m omega by 2 h bar. Alpha is a constant associated with the perturbation Hamiltonian into m0 a plus a dagger n0. So that is m is of course arbitrary here. So that is equal to alpha m omega by 2 h bar into m0. So first term will be a on, so I can write this a acting on n0 plus m0 a dagger acting on n0. I could have written like that. That's equal to alpha square root of m omega by 2 h bar. So first term A acting on n0 will be square root of square root of n into m0 of n. Okay, so I must write n0 minus 1 if you want. Okay, these zeros you have to keep in mind that these are unperturbed states. I don't know what is the correct way to write n0 or n minus 1 0.
So even the coefficient square root also will have some zero suffix.
No, that's not required. I think energy levels we are not. That's why I am not writing n0, n minus 1 0 or something like that. Okay, there is some problem with respect to this notation, but please understand that this 0 is only to tell you that this is an unperturbed problem. Other than that, there is no requirement of 0. Plus, now I can write down root n plus 1 into this m0 and n plus 1 0. Okay, so what will this give you? This gives you alpha root m omega by 2 h bar into root n into delta m comma n minus 1 plus root n plus 1 into delta m comma n plus 1. What does that mean? That means, so what I have calculated, whatever this quantity. So now my En2 will be equal to sum over m not equal to n. So let us call this as alpha m omega by 2 h bar. Of course, I have to square this one into modulus of root n into delta m comma n minus 1 plus root n plus 1 into delta m comma n plus 1. That is what I have evaluated there, the whole square, divided by En0 minus Em0. Now, what does this delta m comma n minus 1 means? In this term, okay, in this term, only m is equal to n minus 1 term will survive, or n is equal to m plus 1, whatever. So m is equal to n minus 1 term, right? So that is equal to alpha square into m omega by 2 h bar, that I can pull out of the summation, and then write terms correspond. So m is equal to n minus 1, right? So that is equal to root n divided by, okay, sorry, root n plus, now m is equal to n plus 1, correct? Okay, if m is equal to n minus 1, then this term will not survive, right? So I will have root n the square divided by En0 and E minus En minus 1 0 plus you will have root n plus 1 the square divided by En0 minus En plus 1 0. Only two terms will be there. Okay, but what is En0 minus En minus 1 0 for harmonic oscillator? That is h bar omega, and this is minus h bar omega. So that is equal to alpha square m omega by 2 h bar, and then there is going to be a 1 by h bar omega that is coming from these energy differences into, I have n square, there will be a minus sign coming from here, minus, sorry, n minus n plus 1. So what does that give you? That gives you, so 1 omega will cancel, and I have alpha square m by 2 h bar square with a negative sign. So now you can see that this result is independent of is independent of these factors. I mean, independent of n especially. Okay, so en of 2 is equal to minus m alpha square by 2 h bar square. Please don't confuse this alpha square to be fine structure constant. This is just coefficient of the coefficient of x in the potential perturbation Hamiltonian. So that means all levels are decreased by this term. Okay. Okay. So now let us look at this problem in a slightly different angle. So now let me write down. So what I have got? I have got is so this is equal to 0, and since it is independent of n, this is also true for all n. Fine. Okay. So now let us look at this Hamiltonian. Okay. So let's look at this Hamiltonian, which is equal to p square by 2m plus half m omega square x square plus alpha times x. Okay. Now, supposing if I write this as p square by 2m plus half m omega square into x square plus 2 alpha by m omega square, 2 alpha by m omega square. Can I write like that? Since I am pulling out this one into x, because the 2 will cancel, m omega square, it will become alpha x. Now suppose if I try to complete the squares here, so this is equal to p square by 2m plus half m omega square into, let's say, x plus um, alpha by m omega square whole square, if I write, minus alpha square by m square omega to the power 4. Suppose if I write like this. Okay, so this I have to put it like this. If I write like this, what does that mean? So if I expand this, it will be x square plus 2 alpha by m omega square into x. So these two terms are present here. Then there will be square term that is extra that I have anyway subtracted. So this we can write it as p square by 2m plus half m omega square into x plus alpha by m omega square the whole square, correct? And minus, of course, I going to multiply this half omega square with this, so minus alpha square divided by 2m omega square, alpha square by 2m omega square. Okay, this is the Hamiltonian. Now suppose if I make a change of variable, so let us say some xi is equal to x plus alpha by m omega square. Okay, if I make a change of variable like this, then what happens? This Hamiltonian will become p square by 2m plus half m omega square psi square minus alpha square by 2m omega square. Okay. Now, so if I am trying to write, h, um, okay, so let us say that So H psi is equal to E psi. Suppose if I write like this, or H psi n is equal to E n psi n. Then we have P square by 2m plus half m omega square psi square minus alpha square by 2m omega square into psi n is equal to En psi n. Okay. Now I could have written this as P square by 2m plus half m omega square xi square into psi n is equal to En plus alpha square by 2m omega square into psi n. I can take this on the other side because this is a constant term. So I could have called this as some En tilde into psi n, where En tilde is given by this. Now this is basically a harmonic oscillator, right? So this is equal to En tilde psi n is a harmonic oscillator. So what is En tilde? En tilde, you will get it as n plus half into h cross omega. Exact. Okay, this is the exact energy level. So what will be your En? Your En is equal to n plus half into h bar omega minus alpha square by 2m omega square. Alpha square by 2m omega square. Correct? Now, of course, now you compare the result that we have got here. Okay, so you compare this result that we have got here. So if you are trying to, so this is the energy that you have got, right? This is the energy that you have got. Now you know that okay, let me just see. M alpha squared
So I think the both values should be same, right? This one and the
yeah, they should be same, but I'm just seeing how that h cross. Okay, I think I made a mistake here. Yeah, the mistake is something here. So the mistake is something like this. You know, your A is defined as square root of m omega by 2h bar into x plus 1 p I times p divided by square root of twice mh bar omega. So this is your x, right? A. So A dagger is equal to square root of m omega by 2h bar into x minus ip divided by square root of twice mh bar omega. So this is this. So now your a plus your x is equal to um, so what will you get if you take a plus a dagger? So a plus a dagger will be equal to 2 times square root of twice m square root of m omega by 2h bar into x. So what will be x? X is equal to square root of h bar by 2m omega into a plus a dagger. Okay, so this is, so I substituted it wrongly. So wherever I have this, I think earlier also I used that. So this one should be root h bar by 2m omega. Okay, so same thing here, root h bar by 2m omega. Okay, so root h bar by 2m omega. root h bar by 2m omega, root h bar by 2m omega. So then what happens? This becomes h bar divided by 2m omega. So this will be h bar divided by 2m omega. So now you can see this h bar will cancel and then omega will not cancel. It will be alpha square by 2m omega square minus alpha square by 2m omega square. Correct? So that will be your En2. En2 is equal to minus alpha square by twice m omega square. So that is what we will have here. Okay, so this is the exact solution. Of course, it is possible to get an exact solution here. Now, whatever we are getting as a decrease in the energy for this problem is because of we can get it in the second order perturbation theory. Okay, and higher order perturbation theory will not give you anything because exactly we have solved and seen that's all that there is a change for the energy levels. So this is an example where you can show that up to second order perturbation gives you the exact value for the energies. Okay, so any questions? Is it clear?
I think this is only specific to this alpha x potentials. If it is alpha x squared or something quadratic or something, maybe change.
Yeah, of course, perturbation theory depends on what is the perturbation Hamiltonian, right? So perturbation theory will depend on what is the perturbation Hamiltonian. So this can be exactly solved only for linear perturbation. Of
So I
course, if
think
it
the
is
same.
x square, then there is no problem. But if it is more than x square, then of course you cannot exactly solve. That is,
So
an
I think
unharmonic oscillator cannot be solved exactly.
yes. So I think I can also treat some problems like this myself, like harmonic oscillator and external magnetic field. We can use that potential as some perturbation, and we can solve it. Or also we can use the same method, like scaling the energy. It's just the energy levels has been scaled down. So
Correct.
when the potential is of the order of this x, can easily do this.
Yeah. So essentially, this particular problem is called displaced harmonic oscillator.
Energy levels are
Displaced
displaced.
harmonic oscillator. Because physically, you know that if you take a spring and mass system like this, right? So let us say this is spring constant k, and then there is an equilibrium length. You call this as some a. Okay, so then this v of x is basically half kx square, r which is equal to uh, half kx square. Let us write like this. Now imagine that you try to hang this in a gravitational field. So this has some mass m and this has mass m. Then the spring constant will not change. What changes is this equilibrium length will change. Okay, instead of so this will be a plus some small value delta will be. So this is the equilibrium length. Okay, so your v of x, because what happens in this case is your force will have minus k. Imagine this is z direction, so minus kz plus some mg. So there is a gravitational force also. Okay, so because of that, in the potential, v of x will be equal to half kx square or kz square plus mg times z. The potential energy will be there. So because of this one, this exactly is like a linear perturbation. And you can see that as you have written here, that our potential, okay, so this is a physical example, The potential that we have seen earlier is V of x is equal to half m omega square into x plus alpha by m omega square, the whole square. So this is the potential of the displaced harmonic oscillator. Now you ask a question, if you plot this, for example, if alpha is equal to 0, okay, so this will be your potential, right? So alpha equal to 0, this is the potential. So this is the potential corresponding to alpha equal to 0. Now for alpha non-zero, what happens? When will this potential be equal to 0? The potential is equal to 0 at alpha at x is equal to minus alpha by m omega square. Okay, so not at x equal to 0. At x equal to 0, what happens? This will be some positive value, right? So that means this is going, and where is that going to be minimum? So you take v prime of x, which is equal to m omega square into x plus alpha by m omega square. Okay, uh, that is equal to 0. That means x is equal to minus alpha by m omega square. Is that correct? So x is equal to at minus alpha m omega square. So that is the point at which its derivative is 0. Okay, so then what happens? So what happens? So when so at x equal to 0, this becomes a positive value, and it becomes 0 at this particular value. Correct? So if you want to plot this, and what is the value of that at this point? That is 0 here. Okay. Plus there is another term. No, what is that term? Minus alpha square by. So this entire thing is your v of x, right? So minus alpha square by 2m omega square. So minus alpha square by 2m omega square. So at x equal to this quantity, this value is somewhat negative like this, right? So that means your this potential for alpha not equal to 0 will be something like this. So this value is minus alpha square by 2m omega square, and this value is minus alpha by m omega square. Okay, so that is what this will give you. So this is exactly same harmonic oscillator, but it displaced from here to here. Just displaced from here to here. That is why this is called displaced harmonic oscillator. Okay, so this is another simple example with respect to this one. Now let's look at a third problem. So let us say that we have considered for hydrogen atom, we have considered H0 as P squared by twice mu minus E square by R. Okay, you may remember that this E square is equal to QE square divided by 4 pi epsilon naught, where this QE is the charge of the electron, 0.6 into 10 to the minus 19 coulombs. We have been following this notation. But we have argued that this is a non-relativistic Hamiltonian, right? Yes. But if relativistic case, or if you have to suppose you are observing the spectrum and then you are finding some deviations and you want to know if the relativistic corrections are important, then we have to see whether such relativistic corrections can be treated what is called perturbatively. So for example, relativistic corrections, okay, so relativistic corrections to kinetic energy, for example. Okay, so energy is equal to square root of m square c to the power 4 plus p square c square. This is the relativistic energy momentum relation. Now if you pull out p square, then this is going to be given by 1 plus p square by m square c square to the power half. Okay, now you can write this as mc square into 1 plus half p square by m square c square plus half into half minus 1 by factorial 2 into p square by m square c square to the power 2, and so on. You have infinitely many terms. This is a binomial expansion. So this you can write it as mc square plus, so mc square, if you get p square by 2m, okay, minus, this will be 1 by 8 into this mc square, that will give you p to the power 4 divided by m cube c square, plus so on. Now what is the kinetic energy? Kinetic energy is equal to E minus mc square, E minus the rest mass energy. So E minus mc square is equal to P square by 2m. This is the non-relativistic limit. And the correction is P to the power 4 divided by 8m cube c square. This is the correction. Okay. So this is, we already have this term. This is non-relativistic correction. And this is the relativistic correction. This is also called the perturbation due to um, mass changing with velocity. That's the relativistic effect, right? Mass changing with velocity. Okay. Now to see, so your Hamiltonian now will become p square by 2m. Okay, so I have been shifting between mu and m. So let us forget about mu is same as m. Let's say p square by 2m minus e square by r minus p to the power 4 divided by 8m cube c square. Now to see whether this can be used as a perturbation, we have to just check what is the order of magnitude. Order of magnitude. So order of magnitude is, you try to find out p to the 4 by 8m cube c square divided by p square by 2m. That is equal to, you have p square divided by 4 m square c square. Okay, p square by 4 m square c square. So if you just look at, so if you write p square as m square v square, so this will be something like 1 by 2 into v by c the whole square. So v square by c square the whole square, which is roughly alpha square, because velocity of the hydrogen atom, we call it as alpha times c. So that is equal to 1 by 137 the square. Okay, and typically uh, for hydrogen atom, this p square by 2m is of the order of 10 to 10 electron volt. Okay, that implies this term, that is p to the 4 by 8 m cube c to the square, will be of the order of 10 to the minus 3 electron volts. So that is the kind of a order of magnitude that is there, and hence this can be actually uh, dealt perturbatively. Okay. Now, of course, you have to ask a question: how do I calculate this corrections for this? Okay, so that is one perturbation. Okay, and then there is something called spin orbit coupling. Okay, so another relativistic effect is called spin orbit coupling. So now you see that so you have a nucleus. Okay, so let's say you have a proton, and then there is an electron. Now there is an electric field. So um, electron is a charged particle. Okay, so electron is a charged particle, and it is moving in the it is moving. So in electron frame, proton is orbiting. What does that mean? That implies um, it is like a magnetic dipole. And it produces a magnetic field. It produces a magnetic field. Now this magnetic field, okay, so can be, let me write this magnetic field P prime as minus 1 by c square into velocity of the electron cross the electric field due to proton. So one can write it in this fashion. Okay, and then electron has intrinsic magnetic dipole moment. Intrinsic magnetic dipole moment, which is given by, that is what, due to spin, or that is called spin. So mu s is given by uh, E by m into spin angular momentum s. Okay. Now you can write down that there is an energy. So this mu s interacts with that B field, whatever that B prime. And what is that interaction energy? That interaction energy, we will call it as some H prime or H spin orbit coupling, which is equal to minus mu s dot B prime. Okay. Now we can ask a question that if you write down your E can be written as or Q times C, that is the force can be written as minus a potential energy V of R by R in the direction of R cap. Correct? Or your electric field can be written as Okay, electric field can be written as minus 1 by q into dvr by dr into r vector divided by r. That is your r cap. So if you go back and write what is your b prime will be equal to minus 1 by c square into v. Okay, so all these things are some scalar quantities. So maybe I can write all of them here. So plus 1 by q into 1 by r into dv by dr. Okay, what is this v? V is basically the potential between proton and electron. Potential energy between proton and electron into, so you have v cross r. Okay, now what is v cross r? So suppose if I multiply, so v is nothing but what? This is equal to 1 by c square q r, and I put a m here, into dv r by dr into p cross r. And this is basically the angular momentum, right? So that is equal to 1 by c square q m, or mc square into q, into 1 over r dv by dr, dv of r by dr, into the negative sign L. Now you substitute it in this expression. So I have spin orbit coupling Hamiltonian. There is a minus sign here, and there's a minus sign here. So I will have, okay, so I must probably call this also as Q. So I can say Q by M into 1 by mc square Q into 1 over R dV of R by dr into L dot S. Okay, so these are all going to give you some function of R. Of course, you have to calculate this. Q will cancel 1 by m square c square and 1 over R dV R by R. Importantly, notice that spin orbit coupling is related to this L dot S term. Okay, so now this, if you want to calculate first order correction for the spin orbit coupling, okay, you have to actually calculate the expectation value of L dot S in angular momentum and spin configuration. Now remember, so please note that we have uh, stationary states of hydrogen atom are common eigenfunctions, common eigenstates, states of Hamiltonian, L square, Lz, S square, and Sz. So these are the complete set of compatible observables for that problem. Okay, but these states are not eigenstates of L dot S operator. These are not eigenstates of L dot S operator. So what do you do for that? What do you do for that? You define a total angular momentum as L plus S. And then you write down J square operator as L square plus S square plus 2 times L dot S. L and S commute anyway. So your L dot S operator can be written as J square minus L square minus S square by 2. So we express the eigenstates of H L square Lz S square Sz in terms of eigenstates of H L square S square J square Jz. Okay. Using to express this, what do we require? Using Klebsch-Gordon coefficients. Okay. Now, eigenstates of this CSCO will be also an eigenstate of L dot S. So if you want to do a perturbation, first order calculation in the perturbation theory, you require to actually calculate the spin orbit coupling. I do not know. Maybe next year you will study nuclear physics. So when you are doing shell model of nuclear physics, the energies, the energy levels, only after implementing the spin orbit coupling result, you will get the correct nuclear levels, which give you all your one of the success of shell model is to explain the magic nuclei, which is related to complete filling of the orbitals. Okay, so this is one problem. You have to calculate L dot S. That means you have to use this Klebsch-Gordon problem completely. Okay, so I've just showed you only the Hamiltonians. Of course, you have to evaluate the first order correction exactly in the same way that I have shown in the previous cases. So those long calculations I will not do today, but you can consult some textbooks if you want to do how to do these calculations. But this is one aspect. In fact, these two terms together, plus there is another term called Darwin term. These terms are called relativistic corrections, and they are giving rise to a term called fine structure, because in spectroscopy, the fine structure is associated with this relativistic correction. Even before all this was known, Schrodinger was able to actually get this form of these perturbation Hamiltonians by very ingenious arguments. He only knows some old quantum theory, but from there he actually was able to show that all this fine structure can be. So it's all phenomenological theory. So that's very bright attempt. Uh, I mean Sommerfeld. So I think Sommerfeld was able to do all that without actually knowing quantum mechanics. Okay, so
Hello, sir.
yes.
And is the depending upon the amount of interaction on the original Hamiltonian, can energy also sense the original energy?
What? Depending on?
Depending on upon the amount of interaction we are adding in form of perturbation, that will sense the original system.
Yeah. So if it is so high that it can change, then you don't use perturbation at all. You can't use perturbation.
Yes, sir. Then what to do, sir?
Then the problem is, see, suppose let's say that we earlier saw that suppose if you apply a magnetic field and put a hydrogen atom in magnetic field, okay, if you put magnetic field so high that electron and proton are torn apart, then it is no longer hydrogen atom, right?
Yes, sir.
So when you are applying magnetic field or electric field, it is weak enough that it is only changing the energy levels little bit. Only then this can be calculated perturbatively. If you alter the system, the unperturbed system is no longer hydrogen atom, it is no longer harmonic oscillator, it is no longer particle infinite square well, then you cannot do perturbation, right? That
Yes,
whole
yes, sir.
expansion breaks down. correct?
Yes,
So we cannot do that. So that is why that smallness of perturbation is something that you have to always verify before you actually do. That is what earlier, if you remember, for many electron atoms, I showed you that even for lithium atom, the electron interaction term is as big as the actual potential. That is why I said perturbation theory cannot be done.
yes. Perturbation has to be small.
It has to be small. Yes.
Yes, thank you, sir.
Yeah. Okay. So let me just do two more problems. One problem is quite long, but let me just see how best I can. Okay. So this is basically the helium atom. So the Hamiltonian for the helium atom is given by P1 square by twice me plus P2 square by twice me minus 2e square by R1 minus 2e square by R2 plus e square by R12, where this R12 is essentially R1 minus R2 modulus. Okay, so you can see this is an electron-electron interaction. Okay, so now let us look at this particular term as H0 and this one as a perturbation. So that is the idea. So so let us just concentrate about ground state. Okay, let's concentrate about ground state. Now you can see, so maybe I will not do the entire calculation here, and I would recommend you to look at Griffiths for detailed calculation. Maybe I will show you some trick of calculation, which probably Griffiths is not showing, but let us just look at the concept. So you know that for hydrogen atom, the ground state energy is minus 13.6 electron volt. Okay. Now for hydrogen, so this is like what? This is equal to minus me to the power 4 by 2 h bar square, correct? Now for hydrogen-like atoms, we know that this Eg is equal to minus m into z square e to the power 4 divided by 2 h bar square, because e square has to be replaced with ze square. Okay, that was the replace e square by ze square. So since I have e to the power 4, I have z square out. So what will that be equal to? Okay, so that is for one electron in helium atom, the ground state energy is minus 13.6 into 4 electrons, because z equal to 2. Now for 2 electrons, that is ground state energy of helium atom is equal to 2 times this. So that is equal to minus 8 times 13.6 electron, which is equal to minus 108.8 electron. So this is the unperturbed. Okay, so this is the estimate of ground state energy for or neglecting neglecting electron-electron interaction. Okay. Now, if you want to treat that as a perturbation, okay, so your H prime is equal to E square by R1. Then we would like to know what is the correction due to perturbation. That means we would like to know what is E ground state of first order correction. We have seen here what is this? This is E ground state of unperturbed energy. That is this energy. Now, how will you calculate this? You know, first you have to know what is the unperturbed wave function. Both electrons are in 1s state. So what will be your psi of R1 comma R2? Psi of R1 comma R2 is equal to phi 100 of R1 into phi 100 of R2. Because in 1s level, they are spins like this, up and down spins, and hence their spatial wave function can be written as a product of this form. And what is the 100 wave function? So 100 wave function is going to be phi 100 wave function is equal to some constant. Let's call that constant to be A into e to the minus 2r. Okay, if it is of R1, it is 2r1 by A. Where A, small a is the Bohr radius. Okay, so now what you have to do to get your E ground state of first order correction, you have to calculate the expectation value, that is essentially integral d3r1 into d3r2 phi star, of course this is phi of r1, phi 100 of r1 into phi 100 of r2 modulus square into E square by R1. Okay, so this is what you have to calculate. Okay, so okay, maybe I simply write here y00 of theta 1 comma phi 1. Y00 is anyway constant, but let me write it like this. Okay, so now what you should do is something like this. This integration is a little bit involved thing, but it's not very difficult. But I want to just show some technique which I believe you would do it in electrodynamics, this kind of techniques. But if you did not do it, let us try to. So this R1 and R2, I can write it as R1 square dr1, and then I will write it as d omega 1. That is the solid angle. And then R2 square dr2 into d omega 2. Okay, so then there is some modulus a square. Let us put it outside. E to the minus 2 times R1 plus R2 divided by A, the square of that one, so that will give you e to the minus 4. Okay, 4R1 plus R2 into y00. Okay, so let us simply write, that is going to give you some constant only. So that constant, let me also absorb in this, into there is also an E square divided by, I have this R1 square minus R2 square, no? So that one I can write it as r1 square plus r2 square minus 2 r1 r2 into cos gamma. Correct? Where gamma is the angle between R1 and R2. Okay, so now let us say, let me define this R large as maximum of R1 R2 and R small as minimum of R1 R2. Okay, if I do that, then I can write this 1 by, so I can pull out R greater, and then remaining one I can write it as 1 plus R small minus R large the square minus 2 times R small minus R large into cos gamma. Now, if you look at this is like 1 by R large into R small minus R large is always less than 1. So this is like 1 plus t square minus 2t cos gamma. So this is a generating function for Legendre polynomials. And hence I can write this as, this is equal to some L is equal to 0 to infinity, R less by R large to the power L into PL of cos gamma. Okay, this technique we will always use in electrodynamics, especially in solving problems associated with spherically symmetric cases. So this is R less by R large to the power L divided into PL of cos gamma. Now, gamma is basically, so it is something like this. We have a coordinate system, and let's say this is your R1, okay, and let's say this is your R2, and this is the angle gamma. But then this R1 can be represented by spherical polar coordinates like this, R1 theta 1 phi 1 and R2 theta 2 phi 2, spherical polar coordinates. Now you can see your cos gamma can be written as, so you write this as sin theta cos phi 1 plus sin theta sin phi 1. Okay, so it is like this. I don't want to show it, you can show it yourself. Cos theta 1 cos theta 2 plus sin theta 1 sin theta 2 into cos phi 1 minus phi 2. So this will be your cos gamma in terms of theta 1 theta 2. Now you have a polynomial in cos gamma. PL of cos gamma is a Lth order polynomial in cos gamma. That also you can express in terms of this, which is a very cumbersome expression if you want to do it. But there is a very nice theorem called addition theorem. Okay, there is something called, this very nice theorem, it's called addition theorem. So you ask a question, what will be your PL of cos gamma? Okay, so PL of cos gamma is a function of theta 1 phi 1 and theta 2 phi 2. Okay, so now you ask a question, what will this be equal to in terms of that? If you ask, it has a very nice form that is given by M is equal to minus L2 plus L YLM star of theta 2 phi 2 into YLM of theta 1 phi 1. Okay, in doing calculations, I have never seen something more useful than this. So this is extremely useful theorem called addition theorem. Okay, one can show this, but more than showing, the amount of simplification that it does is phenomenal. Okay, so now we have to use this here. So now we go back to this expression. We have EGS of 1, that is equal to E square into mod A square. Okay, and integral R1 square dR1, R2 square dR2, d omega 1 d omega 2 e to the minus 4R1 plus R2 by A. Okay, into we have the expression that we have here is sum over L is equal to 0 to infinity, R less to the L by R large to the L plus 1 into sum over M is equal to minus L to plus L YLM star of theta 1 phi 1 into YLM of theta 2 phi 2. Okay. Now only the simplification will occur. Okay, so now assume that there is, so I'm going to write this in this fashion: mod A square integral R1 square dR1 R2 square dR2 e to the minus 4R1 plus R2 by A. Okay, and sum over L is equal to 0 to infinity, sum over M is equal to minus L to plus L, R less to the L by R large to the L plus 1. Now I am going to write integral d omega 1 into YLM star of theta 1 phi 1 into integral d omega 2 into YLM of theta 2 phi 2. Now this integral, if you want to calculate this one, this will be a big polynomial in theta 1 phi 1 etc. Legendre associated Legendre polynomial, and all that is very complicated. But then what you have to notice is that this is into some constant, right? So this is a constant here. Now I can write this constant as, you know, so we know that y00 is equal to 1 by square root of 4 pi. That means you can write down 1 as square root of 4 pi into y00. Correct? So then you can see that integral d omega 1 into YLM star of theta 1 comma phi 1 into 1, that can be written as integral d omega 1 YLM star of theta 1 comma phi 1 into root 4 pi into y00 of theta comma phi 1. Now what does that mean? That means this is like, pull out this square root of 4 pi integral d omega 1 into YLM star of theta 1 comma phi 1 into y00 of theta 1 comma phi 1 is nothing but root 4 pi into delta L0 into delta M0. Only L equal to M equal to 0, orthogonality of the spherical harmonics. So L equal to 0 and M equal to 0 terms are the only ones that are important. And same result you will get from both the integrals. Therefore, this integral becomes very simple now, only radial part. So EGS of 1 is equal to E square mod A square, and then a 4 pi comes from there and a 4 pi comes from there. 4 pi integral 0 to infinity R1 square dR1 0 to infinity r2 square dr2 into e to the minus 4 r1 plus r2 by a, okay, into you have r less to the L is equal to 0. So that means this is not there. So 1 by R large. That's all that we have. Correct. Now you can yeah. So now we don't know which one is larger. Okay, we don't know which one is larger. So what I'm going to do, I'm going to write this as e square mod a square into 4 pi. This one let it. So I'm going to write this as 0 to infinity r1 square dr1 into this r2. I'm going to write it as 0 to r1. Okay, 0 to r1 r2 r2 square dr2. Now 0 to r1, if I write, what will be r2? R2 will be smaller than r1, right? In that case, what will be r greater? It should be r1, correct? So that is equal to e to the minus 4 r1 plus r2 by a divided by r1. This is one integral. Okay, so the second integral I am splitting. The next one is from r1 to infinity. From r1 to infinity. So if lower limit is r1, r2 is greater, correct? So that means r2 square dr2 e to the minus 4 r1 plus r2 by a divided by r2. So like this, if I do and then try to do these integrals, I will get the first order correction in the energy. Okay, so I will recommend you to do this integral. You may have to do 1 or 2 times integration by parts to solve this integral. And if you do this, your integral turns out to be something like 35 electron volts. I'm just recalling from my memory. So some 35 electron volts. So if you do that, then you have 108 minus 108.8, and this is 35. So you will have 8 and maybe 30. I don't know, something like 30. So 8. Okay, so maybe I don't know if I mentioned it here. Okay. So here let me mention this one. So so you can actually make a measurement. So we don't know exact ground state value. So from experiments. Okay, so let me just from experiments. What kind of experiments? Ionization experiments. Ionization experiments. It is known that this EGS is minus 78 electron volts. So this is, you can say that this is the exact, because experiment is always exact. Okay, so we get something which I don't know, you can check the book, but this is of this order, 34 or 35, something like this. And if you do this, you will get your EGS, which is EGS 0 plus EGS first order correction. Okay, so that turns out to be minus 75 electron volt. Okay, so this is something which I remember. So maybe you can just 108, 75. So something like 34 electron volts. I think it is about 34 electron. Okay, 34. So that means it will be 74.8. That is what you will get. Okay, this is not very close, but it is much better than not including this perturbation. Okay, so in helium atom, you get a much better result by including something called a variational technique. So use both perturbation and variational technique, then you will get a result that is much closer to the experimental value. Okay, so that is the thing about this helium atom. Now I just want to bring to your notice only one more problem. That is what is called a Stark effect. So what is Stark effect? You apply electric field. So place hydrogen atom in electric field. Okay, so then what happens? Your perturbation Hamiltonian H prime will be basically minus EE. Okay, so this is QE dot R. So this is your perturbation Hamiltonian. Okay, so in particular, if electric field is applied along that direction, then if you make use of this, then your H prime is going to be equal to minus QEE into Z. So the operator is this Z. Okay. Now we would like to see that what happens to the energy levels. Suppose you say that you have one S state, that is phi 100 of r theta. Okay, phi 100 of r theta phi. Now you can see this is a symmetric function, right? I mean, mod phi 1 square is always symmetric. Okay, so okay, more interesting question let me ask. Suppose if you take n is equal to 2, n is equal to 2, there is a degeneracy, correct? We have something like we have states like this 200, comma 210, 211, and 21 minus 1. So there are 4 degenerate states. For energy E2, E2 of 3. Now if you apply this Hamiltonian, okay, if you apply this Hamiltonian, I mean, if you look at this perturbation, whether the degeneracy in these levels will be lifted or not. Okay, but notice that in this basis, okay, in this basis, this H prime is not diagonal. That means this is not an eigenbasis of this H prime. Okay, so that means these are not eigenstates. So as we have seen in degenerate perturbation theory, H prime. So what we should do, we should find out what is the matrix of this H prime in this basis. Okay, so we must write matrix for H prime in this basis. Okay, that means H prime will be a H prime matrix will be a 4 by 4 matrix. How do you write that? So let's say 200 h prime 200. This is 200 h prime 210 200 h prime 2 211 200 h prime 21 minus 1. So you have this first row like this. Now in this row, this 200 on this side will remain same. 200 200 h prime h prime h prime. On this side you will have 210 211 21 minus 1, etc. You will have 21 minus 1 h prime 21 minus 1. Okay, so I
It's a
repeat that.
it's a 4x4 matrix, sir. 16
4
elements.
cross 4 matrix. Because there are 4 degenerate eigenstates, you have this 4 cross 4 matrix. Okay, so now I will just so let me just use you can use either the wave function or you can argue out. Okay, so for example, uh, you know that this h prime is z, right? So z is equal to um, r cos theta. So which is equal to r into y10 of theta comma phi. Correct? R10 of theta comma phi. That means the parity is negative, minus 1 to the power L, right? That is minus 1 to the power 1 is minus 1. Correct? That is understood because your z going to minus z, you have parity. Now, if you look at the states, okay, so you look at 200, 200. Okay, this is even parity, this is even parity, and this is odd parity, so that will become 0. Okay, and 200 h prime and 210. Um, so like that, you can make some things. So this is, since it is odd parity, it will couple only states with distinct parities. Correct? So that means um, this term will be 0, 211, 200. There will be only some 4 terms that will be non-zero. Okay, so what I'm trying to say is that you can actually get only a few terms. Okay, I don't. Maybe we can do it, but let me see if we can argue. So let us say that I have r21 of r and y11 of theta phi. Okay, so this is a radial part, and then you have this z, and then you have r21 and y1 minus 1 of theta comma phi. So if you have something like this, and then you have integral d omega into r square dr, you have something like that. Radial part you forget, but So this is odd parity, this is odd parity, the product is even parity, the totally this is an odd parity, and hence this kind of a term should go to 0. So this term will go to 0. All the diagonal terms should go to 0. And 2 0 0 h prime 2 1 1. So these three terms, and this is 210 h prime 210. This will be 0. And 210 h prime 211. This also will be 0. 210 h prime 21 minus 1. This also will be 0. So in this case, this term can be non-zero, this term can be non-zero, this term can be non-zero, and all other terms will be. So let's say 6 terms will be non-zero. In this again there will be some other conditions based on which 2 other terms will become 0, I guess. Okay, so anyway, please work out that this matrix completely. Please take this as an exercise. Uh, work out this matrix. And find eigenvalues of the matrix. Okay, so let us say delta 1, delta 2, delta 3, delta 4 are eigenvalues, let's say. Okay, then your perturbed energies E, okay, in this case E2 will be equal to E2 of 0 plus delta I. I is equal to, so I will have E2 of I is equal to 1 to 4. Suppose if some delta I are 0, okay, then the degeneracy will not, fourfold degeneracy will be lifted partially. If all delta I are non-zero, then full degeneracy will be lifted. If some delta I are 0, only it will be partially lifted. So it may have some problem like this, right? Suppose I had 4 levels like this before perturbation. Now this can become uh, 2 levels like this, and 2 levels it may not get lifted. So that means that 2 levels are still degenerate. Okay, so if I remember, I think in this case, this is what will happen. Okay, so that is one situation in which you can have. I think in this case, only 2, totally there will be 3 energies, and one level will have degenerate. Two still will be degenerate. Okay. So, but please look at this. You can again look at any book, Griffiths or I don't know if Sakurai discussing this, but I'm not very sure. Okay, so this is one problem which I partially attempted to show you how to solve, but did not completely solve it. Okay, so this is probably the end of course, and I just wanted to tell you that I'm going to list some books for further reading. Not that you have to read these books for your exam. So there is a volume 1 and 2 by Cohen Kanauji. Okay, so very detailed and very good resource for learning quantum mechanics. Cohen Kanauji, and there is one more author, I don't remember. Cohen Kanauji is a Nobel laureate who got Nobel Prize for his discovery of laser cooling. And then there is a book by Weinberg. Okay, so Lectures in Quantum Mechanics. Lectures in Quantum Mechanics by Steven Weinberg. Okay, and there is an old classic book by Steven Gasirovich. And of course, we should always study Landau Lifshitz. And there are many books. I think at least 500 books will be there for quantum mechanics. Okay, when we studied, there were not many books, but now at least 500 books, minimum 500 books will be there. So I don't know right now what else to write, but general books that many people study, Griffiths, then this Branston and Joachim. Okay, so these are some standard textbook level books, which are also good to look at. But book like Landau Lifshitz or Schiff, these are like masterpieces, which every time you study, you learn something. Okay, so this is some general comments about the list of books. Okay, so I close this here, and I am going to share some two video lectures. Okay, maybe they are there already. You know that competitive exams YouTube channel. So there are two lectures. I will share anyway these things in WhatsApp. But those two lectures, one is on variational principles. Variational, only one lecture, and then the one on WKB approximation. So I request you to go through that lecture, and this is for me to not to feel guilty that I did not cover these things in your class. I'm just sharing that. Okay, so that's all I have. If you have some questions, you can ask. I feel very strange that this is the first time that I have taught one batch, one full semester, and I probably don't know all the names of the students, and have probably if I run into any of you on the road, I cannot recognize, and that's very bad and very strange. Okay, any questions?